Okay, everyone, we should get started. So thanks for joining the Marine Science Seminar. I'm happy to introduce our guest today, Zheguang Zhou, and he is currently a postdoctoral associate at the University of Mississippi, and he's working with Likun Zhang, also at U.Miss, who was the originally advertised speaker, but he felt that Zheguang has done a really good job with this work and thought he should be the one giving the talk. So Li Kun is also on the call with us if anybody has questions. And they've also collaborated a lot with one of our research faculty now, Leo Massaloni. So Zheguang has gotten a bachelor's and master's from Xiamen University in China. And then he has gotten PhDs, actually both from Xiamen and the University of Delaware, where he finished there in 2017. And he's been a postdoc at Old Miss and has even taught a course there in the Department of Physics and Astronomy. His research is in acoustic oceanography and physical acoustics. And he already has a long list of publications and abstracts, and is working on grants and is really doing a lot of research as well as teaching. So with all that, he's going to be telling us about 3D seismic data today. So let's welcome Zheguang.
Thank you, Chris, for the introduction. I wish you could give the whole talk for me. No, good introduction, thanks. So yes, so this is my talk. The title of my talk is Internal Wave Variation in the Gulf of Mexico by Three-Dimensional Seismic Imaging. So this is a project supported by NOAA, Ocean Exploration and Research. And as you can tell, this is a kind of an interdisciplinary research. So we are partnering with Pasa and Leo. They are from the seismic group of this team. And the whole idea of this project is we try to use the 3D seismic data, to image the deep ocean dynamics. This is the project, how I got a job here. And after working with for these years, I kind of have a love-hate relationship with this project. But anyway, I will guide you through the exploration of this project. So when speaking of the imaging the ocean water column or using traditional oceanography measurement, it's quite challenging. If you think about this way, take the in-situ measurement, for example. For traditional measurement, we have the CTT profiling, or we use buoys, floats, and moorings, or some people use underwater gliders. All these measurements, I would consider they are only 1D, one-dimensional. You take a vertical profile for the water column. Some people argue that underwater glider can be considered 2D, but they are semi-2D. Anyway, so the challenge here is usually with these kind of in-situ measurement profiles, they often use very poor spatial resolutions, especially on the horizontal direction. Let me give you an example. For instance, if we consider a CTD profiling, let me use the pointer. If you consider the CT profiling, if you want to get a 2D image of the water column, what are you going to do? We probably need to take the profiling at one location, travel a few meters away, and then take another profile, and travel to the other location, take another profile, something like this. But consider the size of the ocean or the area of your research. This can take quite a long time to collect. So the final image you get, it's usually the horizontal resolution will suffer. Nobody takes a CT profile for every 5 meters, right? Usually they kind of more than 100 meters, a few kilometers away. So this kind of the problem is they yield very poor spatial resolution. And the other important measurements oceanographers often using is remote sensing. This is great. This is brilliant. It can directly measure the 2D image from the surface, and you don't even need to go into the ocean. So I think it's very good. But the problem for imaging water column is that, as you can tell, the satellite is mostly limited to the sea surface. For the deep ocean dynamics that doesn't produce surface signature, the remote sensing won't work. So it cannot be used to image the vertical water column. So if these are not the approach, then how? So in this study, we use a technique called seismic refraction imaging. So this cartoon here kind of gives you an idea. As the seismic vessel traveling, like towing the receiver array from the left to right, it emission like low frequency sounds, and those sounds will penetrate the seafloor. And think about if the seafloor have different layers, they are producing different acoustic contrast, impedance contrast. That contrast will reflect the acoustic signal and then get received by the receiver array. And after that, we collect the data, we can do the processing, we kind of get this beautiful, nice image of the water layers. So this is kind of how the seismic imaging works. They have all long been used by geophysicists to study the ground, also used by the big oil companies to locate where the oil reservoirs are. It's a well-developed technique, actually. So the idea is here. If we can image the ground layer, can we image the water layer? Think about the ocean. Usually we consider they are stratified. That means the ocean can have different layers. Take this image, for example. Say if there are some warm Mediterranean water intruding into this region, that will kind of create a different layers, right? Once the acoustic signal hits these boundary of the layer, they can be reflected back and received by our receiver. The seismic receiver they usually call streamer, but anyway, there are acoustic receivers that can collect the reflection of sound signals. And we have that data, we can do the imaging and get the image of the water column. That's the idea. But the problem is usually these water layers, they produce much weaker refraction than the ground layer. So previously, these data, water column data, they kind of ignored by those geophysicists when they are trying to study the ground, because these signals, they are really weak compared to the ground layers. But this is what we focus in this study. So with this water column refraction, let me show you what the water column refraction data would look like. So the left figure kind of shows the acoustic signal, the seismic data. Usually they are organized in arrival time, because when we receive the data, we know the arrival time of the data, and we have multiple receivers. So these are the receiver from different, from the streamer. We have multiple receivers from the streamer. And for the acoustic arrival time, they can tell the different paths. They have a path traveling directly from the sound source to the receiver. That's usually travel along the surface. So you can consider this as a surface boundary. And also we get a signal reflected back from the seafloor. That kind of create another lower boundary. And the water column refraction is between the sea surface and the seafloor. So it's kind of in this region. And we can see, if we see closely, we can see definitely there are some features in this water column refractions. Although the amplitude here is much lower than the seafloor, it's much stronger. But there are plenty of features. And if we do some imaging using this portion of the data, it may end up like something like this. For example, this is just an example, not exactly data. No. So this shows the seismic imaging of a water column portion data. And here it shows the internal wave beams along a continental slope. So these internal wave fields, they are very weak. They probably cannot be seen from the satellite image. Also, they are subsurface. But with seismic imaging, they can produce these very nice image, tell a lot of detailed structure about these waves. If you zoom in, they kind of these are internal wave beams reflected off the continental slope. So image like this could be very useful for oceanography studies. So this is how it leads to the whole idea of seismic oceanography. So this seismic oceanography is a interdisciplinary subject between the explorational seismology and physical oceanography. Basically, they are trying to use the seismic data to study physical oceanographies. So it all begins in 2003 when Holbrook published a paper in Science. So in that paper, they reported that the thermal highline structure of a wavefront can be imaged by a seismic reflection profiling. So if you look close, they really show very high resolution details that would be very hard to get from traditional oceanography measurements. So the idea when virus and people start to follow their work and use this kind of technique to image eddies, internal waves, and other kind of stuff. And they also develop a lot of imaging analysis techniques. For example, they can resolve the wave spectrum from these imaging, and also they can resolve the geostrophic current velocity from the imaging. So this image kind of shows the vertical current, geostrophic current velocity for an eddy, but this is kind of vertical section. It kind of cut the eddy into half, kind of the idea. And they can even analyze the diffusivity for that part. For instance, there's a seamount, they kind of look at the turbulent diffusivity around that region. And the analysis keep adding more and more as times pass by. So it's very powerful tool, and it has been applied to a variety of ocean dynamics. In fact, the fundamental advantage of the seismic imaging is the resolution. So here kind of shows this idea. The left-hand side is an imaging constructed by CTD profiling. The horizontal resolution here is probably larger than 100 meters. On the right-hand side is the seismic imaging. Okay. Oh, by the way, these imaging both for the Mediterranean eddies, big circulation of the water. The resolution from the seismic imaging is a lot higher. It's like 5 meters. So this could be very useful for studying the fine structure of ocean dynamics. And this image shows kind of the scales of the typical ocean dynamics. They don't show you like a very small ocean dynamic. They kind of show the submeso scale from to the global scale. Anyway, so I would like to show this image because I want to highlight what portion of ocean dynamics can be imaged by the seismic. These ocean dynamics have very large spatial scales and very wide time scales. But for the seismic imaging, we can do is mostly focus on this area. It's like internal waves, internal tides, some upwelling currents, eddies, fronts, things like that. From spatial scale, it probably covers from a few meters up to 1,000 meters, 1,000 kilometers, depends on how long the seismic survey will take. But usually it's kind of this area. So these are the ocean dynamic we can image. So am I suggesting that we just, if we want to study this ocean dynamics, we go and do the seismic survey? No, that's not what I suggest. So what I suggest is we use the existing marine seismic data that has already been collected. In fact, the oil company has already, the oil industry already collect quite a lot of amount of marine seismic data. So this is an example from one of the leading seismic surveying company called Schlumberger. And they even have a seismic data library for that. So in this library, they have 2D data and 3D data. They have more than 3 million kilometer 2D data, more than 3 million kilometer 3D data. And they also have this more than 17,000 years of combined technical expertise. Great. I don't even know what that is. But the idea here is they kind of have a lot of data and a lot of knowledge about those seismic data. So let's take a look. They have the data from Gulf of Mexico. They have data from Latin America, Europe, Africa, South Asia, and even Australia. So they acquired all of them. Here, let me give you an example. This is one of their data they have in the Gulf of Mexico. The area here kind of shows the area that covered by 3D data, 3D seismic survey data. And these lines are like the 2D surveying line, the 2D data are. And we can see they kind of have a lot of data along the coastal area or the continental slope areas. And these are great because there are a lot of features occurs in the continental areas, margins. So if these are the oceanography data, this can be very useful for understanding the water mixing in these regions, as most of the water mixing does not occur in the open ocean, but occurred in the kind of the continental margins with the interaction with the seafloor topography. So these are great data. And so we have this idea, we ask them and for kind of an area of data in here. So this image kind of shows where the 3D seismic data we request are. So they are in the northern Gulf of Mexico, near the continental slope region, somewhere here, right outside this Mississippi River Delta. And we pick this continental slope region. I have enough figure for that. If you zoom in, you can look in kind of the detail. So we requested the data in somewhere near Mississippi Canyon. The block number is MC14Q. So if you want to request the data, just in case. So they give me an area of 25 kilometer by 25 kilometer area seismic data. And along this continental slope, the depth, water depth changing from 780 meters to 1,200 meters. So it's along the continental slope. And we pick this, have some interesting seafloor topography here. Hope we can see some very interesting ocean dynamics there. And because the 3D data, it's an area. How they do it is they take seismic survey like line by line. Okay, they do this line, probably they will come back and surveying the other direction and come back. So they do something like this, zigzag surveying this area. So as you can tell, it probably takes quite a long time to collect 3D seismic data. In fact, the data we receive cover a temporal domain from August 2002 to February 2003. So this kind of show you kind of the date time distribution of our seismic data. So the line number here corresponding to this line number. So if you say line 102 2000, it probably is 2000 somewhere like this line, for example. So for this 2000, it probably is measured by late October 2002 at the time during that frame. So yeah, this 3D seismic data cover a very large time range. And we, very interestingly, in this data, we identify a range that we call it linear acquisition period because all these lines and the acquisition time, they kind of progress linearly. So we will use this portion of data for the analyzing later on. But we are glad to see in our data we have this region. So the other difference between 2D and 3D seismic data is not just the surveying direction, it's also the configuration of seismic survey. So this kind of shows a example of that. For 3D seismic survey, they not only have one streamer, they have multiple streamers like this, and they define a direction. So the direction that along the ship's sailing direction, they call it inline direction. The direction that perpendicular to inline, that they call it crossline direction. So we already understand we can use the inline direction streamer data to get an image. But if you think about the crossline direction, say these are all the receivers from each streamer. If you're thinking about this way, they're also collecting data for these planes. So for 3D seismic, they end up with an image not only like this direction, they also have image like this direction. So they can get a whole volume of this area using this seismic survey. So this is not exactly what our seismic survey looks like. I couldn't find a figure for that. I'm sorry about that. In our case, we only have 8 streamers. We only have 8 streamers. This is probably more than that. And the whole 8 streamer area, they call it a swath, a seismic swath. That means the cover area by this seismic streamers. For each streamer, it's about 8 kilometers long, and each streamer have 640 receivers with a spacing of 12.5 meters. So these seismic geometric configuration is fixed for our seismic data. And with that configuration, we can collect the seismic data and then processing them with the seismic processing technique. So this kind of illustrates how the seismic data processing work when doing the imaging. Thinking about that, here is a 2D seismic array example, but the 3D is similar idea. So I'm illustrating the idea here. 2D is much more simple. Say if there is a seismic vessel, they towing a seismic streamer like this, and the sound source is somewhere here for the air gun. They use air gun, produce low frequency sound signals. Say there is a guy here can reflect the sound signal. So the sound signal travel from the source, hit by this guy, and then return and received by one of our receiver. A few seconds later, the ship will keep moving this direction, and it will be picked up by another receiver, like a later receiver. They are from the same guy, from this object here, and if you keep doing this on and on, you end up with something like this. You can have multiple reflection from one object, and in seismic term, they call it as common midpoint. And the key of the seismic data processing is using these common midpoints to get the information about this object. Does it reflect the sound signal? How strong it reflects? So they first saw the data into the common midpoints. So they pick out these, for instance, the shortest one probably is the first one. They have the shortest arrival time. Longest path, longer arrival time, arrive later. So it end up like something like this. They call it a common midpoint gather. The seismic data will first sort the common midpoint, and then they perform a process called normal move out. Normal move out is try to, because we know the seismic configuration, we can account for that. We adjust the arrival time difference for these common midpoint data, make them to align at the same arrival time. After that, they can perform something called stacking. Basically, that's the average of all these signals. So the averaging will cancel out a lot of random noise and leaving very clean signal for analysis. Finally, they process a step called migration. They can take all these stacking and construct in an image, and they converted the two-way arrival time. Usually the vertical axis is two-way arrival time to depth. They use the sound speed velocity model to convert that time to depth, and they also convert a common midpoint to distance, the horizontal distance. So end up with an image something like this. So this is an image from Holbrook's paper, kind of illustrate why the seismic imaging represent the water column layers. So these are the black and white are the seismic imaging, and this line here, white line here, is the measure sound speed profile, and they kind of find this reflection has a interesting relationship with the sound speed profile. When the sound speed profile has some different structure, they correspond to different like curvatures of the seismic images. So for 3D seismic data processing, the idea is the same, but the processing would be much more complicated. I'm not going to dig into deep of that. So this kind of show a workflow of the 3D seismic data processing. These processing 3D data, they are resource consumers. So our seismic teams, they even use supercomputers to process them. Otherwise, it could take quite a long time. Anyway, I have zero contribution to that. So after the hard work, after the tears and sweat of my seismic colleagues, we finally get some very nice seismic volume. This is the final seismic volume. The cartoon playing here kind of guides you through different inline, what it look like. So I will let you guys take a look at that. So kind of shifting different inlines, and because it's a volume, you can adjust. Okay, it's a volume. You can kind of look at in 3D and have different features. And they overlap with the seafloor. So the imaging is actually quite accurate. If you consider seafloor, they match well. But our focus is these ocean dynamics imaged by these volume, these seismic. So this is another view of our seismic volume. This shows the kind of the horizontal slice, horizontal sections of our volume. So they kind of switch in different depths. And because there is kind of a trench there, so kind of we hope there are some interesting dynamics. Okay, kind of hope this video give you some basic idea about our seismic volume. Yep, there are a lot of features in these volumes. Next, we are thinking about analyzing the seismic images. This is also when I was first come here, this is also a kind of a very new project to me. I'm not a seismic person, so I guess you are not as well. So let me introduce the kind of the orientation they're using in the seismic data. They as I already explained, they use inline, which is along the seismic vessel, and also coastline, which is perpendicular to the inline, to represent seismic image. So the final image, seismic image, also organized in this way. So this is the inline direction, like here, and they have a cross section that called crossline image. And because it's 3D, we can also put a horizontal slice. This they call it depth slice image. So I'm going to show you inline, crossline, and depth slice one by one, so you can get a better idea of how 3D seismic image would look like. So this one is shows the inline seismic image. I show 3 different inlines here. The vertical axis is the water depth. The horizontal axis is the lateral direct distance, or you can think that the kind of horizontal distance of this image. I want to point out the vertical depth is vertically exaggerated. It has the exaggeration considering the aspect ratio of the ocean. Usually 1 kilometer horizontally doesn't mean much, but 1 kilometer in depth is kind of important. So it has the exaggeration in vertical direction. And showing these 3 inlines here. And these are the seismic images. A quick information about how we can see this seismic image. What the seismic image represent is the acoustic impedance contrast of the water layers. In terms of oceanography, that's related to the temperature gradient, the vertical temperature gradient of the water column. Here, the color doesn't matter. No matter it's red and blue. Some people use red and blue. Some people use black and white. Some people even use other funny colors. Totally depends on their mood. But the intensity here is more important. The intensity here kind of show if you see a strong red or strong blue, that means the vertical temperature gradient is large at this location. So why here we see these very large reflections? Because usually this depth is the thermocline. So they have big temperature change that can produce significant refraction of the sound signal. And if we go deep, the refraction gets smaller and smaller because the vertical temperature gradient is reduced. Because these are 3D seismic data, we can see from different inline. We see that different inline image kind of show very diverse ocean dynamics. Even though our area is very small, like 25 kilometer by 25 kilometer, it's not much. But we kind of see very different structures in this image. Why, you may ask? Because in fact, this image represents different times. So let me back up. These data, they say they are taking this inline on this date. The other inline, the data may be collected by the other date. For instance, this is October 20th, this is 24th, this is 28th. So this is 4 days apart, this is 4 days apart. You can see that between these 8 days, the water column has gone through a big change. Kind of like that. The idea is like that. But what caused the water column? What ocean dynamic caused this big change of the water column? It's something we're going to figure out later. But from seismic image interpretation, that would be during these 8 days, the water column is kind of have the thermal client is weakened, the stratification level probably is reduced during this period of time. That suggests probably a big mesoscale ocean dynamic occurs in this region. That's the inline. Then let's take a look at the cross line. So the inline here, now we look at the perpendicular direction, cross line. You may think the cross line image is the same as the inline, but in fact, they are not. This is a cross line image. I also use the vertical exaggeration here. The first impression is that the quality of the cross-line image is very poor. It's not like inline, we can see very clean, clear ocean structures. This is kind of the first impression when I saw this cross-line image. They are kind of break into different pieces, and there are strong discontinuity here. It doesn't show any features. So that kind of puzzles us a lot at that time. But why, you may ask? The reason the quality of the cross-line imaging is so poor is because there are these different lines they are collecting at different times. So for these data, it suggests that there are temporal variations in these image. For example, if we zoom in these two regions, we can see at the shallower depths, there are a lot of discontinuity, but in the deeper part, it's kind of more continuous. Why? Because in the deeper part, we will consider the ocean dynamics usually have longer time scale. Because for the shallow part, it's affected by the surface wave winds. They kind of have much smaller time scale ocean dynamics. And you may also ask why this part looks kind of different from the other part. That's because of time shift is different. For here, they are kind of continuously measured. But here, there is a big time drop. For instance, this point to this point, there is 2 months time drop. So you can see there is a big change in the water column. So this is another evidence that shows that in the cross-line image, they have temporal variations. Finally, let's look at the depth slice, which is the horizontal cut. In the depth slice image, we showed 3 different depths. 2 important informations. First, we see this horizontal horizontal stripes. These are the seismic swirls that only appears in horizontally. So the horizontally is the inline direction, they are continuous. But if you look from the vertical direction, that's the cross-line direction, it's kind of showing different swirls across different swirls. And as the second information is, if you go deeper down, this swirls effect is not as significant in the deeper part. Again, this is agree with the time scale of the ocean dynamics deeper part kind of have longer time scale. So all these seismic images kind of suggest that the temporal variation only appears in the cross-line direction. So this kind of the image showing summarize that idea. The temporal variation only appears in the cross-line direction, and there's no or very little temporal variation along the inline direction. This is kind of a simple idea, but it takes us quite a long time to figure this out, as this is an interdisciplinary research. And the next question is, okay, we see these features from the image. How can we quantify them, or can we see the variation, can somehow show this variation from the data? And how the ocean dynamics, the temporal variations, spatial variation of the ocean dynamics project into this seismic images? Why? There are a lot of questions to ask. So let me give you a very simplified example that how the temporal and spatial variation of the ocean dynamic can project into our inline and cross-line seismic images. So consider a very simple word column variation, like 1 cycle per day and either 1 cycle per kilometer. I use very simple number here for illustration. And using a traditional 3D seismic survey configuration, sailing speed of 2.5 meter per second, and acquiring 1 swath per day, and 1 swath equals 0.5 kilometers. Okay, use this configuration. If we try to get an inline image of 1 kilometer, we'll go through one spatial cycle here, the blue one. Sorry, it overlapped with the black one. But for the time, 1 kilometer only equals to 7 minutes. So that's 0.0005 temporal cycle. So it's way less than 1 cycle. It's probably nothing. So if you add these 2 up, you end up with the black curve. So the total variation is mostly represented spatial variation for inline. Now let's move to the cross line. For the spatial variation, 1 kilometer, yep, it's also 1 kilometer per cycle. But for the time, to survey 1 kilometer cross line image, we probably need to take 2.5 swaths. That means 2.5 days, 2.5 temporal cycle. So you have some temporal variation cycle here. And if you add these 2 up, you end up with the final variation, something like this. So we can see the total variation is way different from the spatial variation. The temporal effect is very significant here. So this kind of give us an idea if we can look at the variation between inline and different cross line, what it would be. The idea here is the temporal variation will add fluctuation in the cross line direction. I use one number here, but if we change the number for other mesoscale ocean dynamics and using the exactly the same seismic setup, we end up with similar idea. Even though I'm not illustrate here, but this is the idea we get. The next question is how. Okay, that one is too simple. The next question is how can we quantify this from our seismic volume? We cannot get simple variation like that, right? In fact, we can. We can use the cross correlation to do that. Say if we want to understand the variation along this inline direction, what we can do, we can cross correlation data along this direction. So we choose different section of data and do the cross correlation for them. Same idea for a cross line. If we want to analyze the variation in this direction, we can take the other part of the data and do the cross correlation. And it end up like something like this. So the idea of using cross correlation is something like represent the similarity between seismic images. So for inline direction, the similarity fluctuate like this. At the beginning, it's 1 because it's exactly similar to itself, right? But as you progress, as you move into different sections, the similarity will quickly decrease and then fluctuate. Similarly, for a cross line, it's the same, but you can see there are some fluctuation difference between the inline direction and also the cross line direction. And this is the correlation length for inline and the cross line direction. Inline have a longer correlation length. That means it takes a longer time to decorrelate. And the cross line, the correlation length is much shorter. And recall that we know that for a cross line direction, the variation will have more fluctuations. So if this kind of match our previous simple examples. Next, if we do the Fourier transform of these variation, what would the result be look like? So this is the spectrum doing the Fourier transform for inline and cross line variations. The blue one shows the inline here. The red one shows the cross line. Overall, the two correlation have same trend. but we see that the cross-line correlation have all these small peaks. These little peaks are responsible for that added fluctuation in the cross-line direction. And one interesting peak we see here is we kind of see this big peak here. Actually, it corresponded to the M2 peak, the kind of the semi-diurnal type cycle. And we think this is an evidence of the temporal variation, because thinking about our seismic study region is near the coastal regions. The dynamics there is probably heavily affected by the tidal cycle. So this could be an evidence for that cross-line represent the temporal variations. So the take-home message here is only the cross-line direction has the temporal variation, and that will make our image, inline image, into represent the snapshot of the ocean water column at different times. Sorry, it's a bit complicated, but we are going to move on to the fun part here. We know that idea. Now we can safely use that knowledge to study the internal wave variation in our seismic data. So here, what I show is our observation of internal wave variations in our region. So these different images shows the snapshot for different time. The spatial difference here, they are not very far away. It's like only 400 meters apart. That's 1 kilometer. So in terms of ocean dynamics, probably that's not much in the horizontal direction. But we can see the water column is going through like very big change here. At the beginning, they have very strong thermocline weekends, and in the deeper part, they kind of have a lot of new waves generated here. And yep, so this part, we are more focused on this part because we are focused on deep ocean dynamics here. And these are more images from different times now to October 27th. The water column is even weakened, and these internal wave, they kind of randomly shows up here. So this is very interesting. Can we do some imaging analysis and get an internal wave spectrum from this? The answer is yes, and this is how we do it. To get an internal wave spectrum, the first step is we kind of select the area, define the area, take the data from that area, and then we track these curvatures. I'm going to skip the details of how we track these, but basically we can track these curvatures. We track both red and blue curve here. Unlike other study, they usually track one curve, but in our study region is kind of limited, so we try to include as many curvatures as possible. So we track both, and finally we can gather curvatures. We can calculate the spectrum from these curvatures, and we end up with 3 spectrum. One from the red curve, the other one from the blue, and the black one shows the average. And very interesting here is the gray line here is the internal wave slope, usually the theoretical slope for internal waves. It's a negative slope. We are glad to find that our data also have this slope. That means these are really internal waves, internal wave fields. And then we apply that to all the inlines, and this is what it looks like. So this we apply that analysis to multiple inlines. When we all find this our data, we have this similar slope. That means, okay, mostly in our region, those curvatures are kind of match the internal wave spectrum slope. Great. And with 3D, we have the time information. We can do one step further and kind of give you a temporal view of these spectrum. So from October 20, it's kind of like this, and kind of have some lower frequency, higher, this is lower frequency components increase here, and something like that. You can even get a temporal view of that. Then from this internal wave spectrum phi here, we can estimate the diagonal diffusivity. This probably is the most boring slide of my presentation, so bear with me. From spectrum to diffusivity, the basic idea. Okay, I put a equation here, but let me explain kind of the idea. The diagonal diffusivity is proportional to the dissipation rate of the turbulent kinetic energy, and that energy can be calculated from our internal wave spectrum compared to the GM76 spectrum. So we have this, we get a spectrum, we have this, and this can be generated from some typical GM76 model. And we get this, we can put back all the parameters and get a diffusivity. So this is kind of the idea of how we do that. We follow the methods in this paper, just in case you are interested and want to do it yourself. And let me show you the result. So this is the result of diagonal diffusivity we get. We kind of have a range from minus 10 to the minus 5 to 10 to the minus 3. And the result from the red curve and black curve, they kind of very similar. They have similar distribution, and the correlation is even pretty good. It's 0.4 something. And that means if we average these up, we can have a better estimation of the diffusivity in this region. So we have the spatial, we have the space and temporal information. We can create a map, the temporal spatial map of the diagonal diffusivity. And this is what it looks like. So for each pixel in this image, we calculate it from the curvature we check, and we estimate diffusivity and put a number here, represent as a color. So this is kind of how we get the whole image. And because inlines corresponding to different time, we can represent them as time, and we can calculate that for different depths. So it does something like this. So let me summarize the important information in this image. First, we found that the diagonal diffusivity kind of increase with the depth. If we go deeper, we will have a larger diffusivity. Why? Because we are getting close to the seafloor, and there are probably more waves generated that will increase the diffusivity. But in terms of time, it's a bit complicated. So let me separate them into two different water columns. The first part, let's use 600 meters as a boundary. So this part is for the shallow part, and this is for the deeper part. Let me show you the temporal variation of this diffusivity. We can see for the shallow part, it doesn't really change much. For this portion, it doesn't change much over the time. But for this part, we kind of have an increasing diffusivity for the very deep ocean. That means there are probably internal waves generated very close to the continental slope during this period of time. And next, we want to figure out what's responsible for this generation of internal waves during this period. Let me go back. So this is kind of the location where we are. The water dynamics in this region is dominated usually by the loop currents in the Gulf of Mexico, and also the Mississippi River outflow. And because it's a coastal area, probably it's also related to the tidal dynamics. So we think there are three dynamics: tide, river plumes, and eddies can generate the internal waves. The tide will induce currents along the continental slope, and study has shown that they can generate internal waves. But the question is, is this tidal generation internal wave response for our increasing diffusivity in this region? My guess is probably no, because I would consider if that's tide, that's probably it doesn't change like this in a few days. Probably there's something else. But yes, there are some internal waves are generated by tide in our image. But for this, in the whole increasing process, I don't think the tide is responsible for that. The second possibility is river plume. Some research shows that when the freshwater river plume usually is associated with big flood in the river. When there's a big flood, when the flood coming out, it meets the seawater. I kind of make the dip for this mixing there and creating internal waves. So this is our image for that. The river plume come out, they generate internal waves. That's another mechanism. And our location is very close to the Mississippi River, so it's possible. But we check the Mississippi flood history. There's one big flood in April 2002, but our image is kind of for 6 months, 6 months later. So probably it's not because of the river plume, because the time doesn't match here. The last possibility is the eddies. So eddies are everywhere in the Gulf of Mexico because of the loop currents. Big, small, they are kind of have this vertical structure, something like this. You see a circulation in the surface, but it can penetrate to deeper parts. And when it moves north and hits the continental slope, it's affected by our slope and will generate internal waves. So we guess this is because the eddy, and it's possible. And how we verify that? We can check the satellite image. So this is the satellite image during that period of time, October 16th to October 30th. The color here shows the sea surface height anomaly, and the arrow here shows the geostatic currents inverted from SHA. And we see that they kind of have this this anticyclone eddy near our seismic region. And as the time passed by, kind of approaching us. So this is a time frame for seismic for the satellite image. And if we over that with our time frame of what we observe, we can see during this period of time, when it approaching, we kind of see for a deeper water column, the diffusivity increase over this time. So we think this is the most likely mechanism for generating the internal waves in this region for that period of time. And yes, the satellite image is very powerful, but from the beginning of the talk, it kind of doesn't work for image of the water column. But in this study, we can show that this is kind of during that period of time, the water column structure changed during that period. Okay, the thermocline kind of weakening during that period of time and generating a lot of internal waves in the very deeper part, because the deeper part of the eddy will hit the seafloor at a big first. So it match our result, match the satellite results quite well, I would say. Okay, to summarize this talk, let me give you 3 take-home messages. The first, I hope that for this in our talk, I convinced you that the 3D seismic imaging is a very powerful tool for studying deep ocean dynamics. And the second one is the temporal variation really exists in 3D seismic imaging, and it only appears along the cross-line direction. And that's good, because it allows us to image the inline as the snapshot from different moments, different times. And the final take-home message is that internal evolution at a continental slope can be resolved from 3D seismic imaging. And our results kind of agree with the satellite observation of a nearby eddy. So I think it's a very powerful tool. We have explored this. We try to understand this we take a lot of efforts. This is what we have so far. We were very pleased with our results. And finally, we would like to thank NOAA for this project, and also to thank the SRAM Beijing for donating the 3D seismic data and also the seismic processing tool. And I would like to thank all the audience for listening to my talk, and I will try my best to answer the question you have. Thank you.
Okay, thanks so much, Zheguang. We are a little bit over time, so we understand if people need to leave, but for those who want to stick around, let's take a few questions, and you can either raise your hand or type in the chat or just go ahead and unmute.
So I have a question, Zheguang. A very nice talk. Pretty cool. You can get diffusivities from this data set. You show there's a peak at M2, but can you say something about the frequency content for these waves that are generated due to mesoscale flows? I suspect there's like a diurnal peak for the local inertial frequency. Is that right?
Very good question, Martin. Yes, this is very, there are a lot of information in this variation spectrum. To be honest, we don't fully understand it yet. This is what we get from our volume, and the M2 peak is kind of easiest to identify in this case. And comparing these two directions, I think these peaks are responsible for the different time scales, different temporal variations, but we kind of don't know yet what they are. But yeah, we don't quite know yet. We are still exploring this.
And so my sort of follow-up question is that, so you find these diffusivities at this location, right? But of course, people have estimated diffusivities using microstructure and fine structure and all that in other places in the world. So do your diffusivities that you find close to the topography, do they agree with other findings in other locations?
So for the diffusivity estimation, they have all different methods. Our range is like it's kind of have a wider range in this area, and we follow this methods using the Dickinson paper, and they also discuss about the diffusivity measure from seismic imaging and also from other different methods. There is not 100% agreement here. We kind of have that. Oh, by the way, our estimation is slightly higher than the Dickinson paper. We think that's because we are more close to the continental slope, and their paper, they kind of have actually, I can show you the paper. So this is the method we are following using this paper. They are published in Zheguang Oceans. They also estimate the diffusivity map. So they kind of cover a much larger region than us. So they kind of have lower diffusivity than we are. When it's very close to this region, our result is more like this region. So we kind of have a slightly larger value than this paper. But in his paper, he also compared the diffusivity measured by other methods. The order is pretty close, but the value is not. It's not. So they argue that probably because of different methods, there are still something need to be figured out. But so far, what we can compare is this paper, and I think our results match their results quite well. That's all I can tell so far. But there are not much diffusivity data measurements we know for this region.
Okay, other questions?
Hey, Chris, I have a question.
Sure.
Hi, Zheguang, 我叫张晓东, and so my question is this: you spend a lot of time explaining cross line, but when you do this added diffusivity of the internal wave, do you use both inline, cross-line, or just use the inline?
Thank you, Dr. Zhang. Very good question. I was attempting, it's very attempting to use the cross-line image to do all the analysis. But after understanding there are temporal variation appear on the cross-line, we stopped using that. Because if you go back looking this image here, it's breaking to different times. So this is combining the temporal effect and also the spatial effect. So the diffusivity, I can't even track curvatures in the cross-line image. All these curvatures, they are very short. They are break into very short pieces. So I know it's very tempting to use the cross-line image. And for seafloor imaging, they use cross-line image very well all the time. If you look at the seafloor is very continuous, because thinking about seafloor, it has very long time scales, thousands of years, millions of years. So it doesn't affect them at all. But for water column imaging, this cross-line image, we cannot use them right now due to the temporal effect. So that's kind of the message of our temporal spatial variation analysis is that currently, probably the biggest advantage of 3D imaging is not the cross-line, but the inline. We can view inline with snapshot from different times. So we only, back to your question, we only do the diffusivity estimation for inline image. I personally think we cannot use that for cross-line, given this temporal effect heavily appears in this region. But maybe there are other water column, other part of the ocean that have time scale. Maybe cross-line analysis is possible. That's my answer to your question. I hope that answers your question.
No, I absolutely you answered. But actually, I'm thinking if you have an inline taken at a different time, then there's no need to look at the cross line, right? It's inline taken at a different time, it's also give you temporal resolution.
Yes, that's right. So that's why we are using inline only. For the seismic people, they use cross-line because they want to see the feature along this direction. And at the beginning, we are trying also want to see the feature in this direction. But our conclusion right now is we cannot resolve that from a 3D water column seismic volume because they are heavily affected by this temporal effect.
Okay, thank you.
Thank you.
Okay, anything else? You mentioned at the beginning you had a love-hate relationship with this project. Did you tell us everything that you loved and hated about it, or?
Yeah, I love new project and I love oceanography project. That's for sure. But the hate relationship is kind of they are when I'm doing the exploration, it's kind of hard. Sometimes I have no clue. Right now the talk is like 45 minutes. Kind of okay, we go. Everything now is pretty clear to me right now. But when I was start doing it, I don't have a seismic background, and the seismic people, they don't have oceanography background. They never understand how this temporal effect can affect the water column imaging because they do that for the seafloor all the time. This seafloor doesn't have this. They are even trying to improve the cross-line image so that we can use them for analyze one day. And I was also convinced by them to try that at that time. But after we kind of clear out all the things, we get to the conclusion that that cross-line image probably is not going to work the same way like seafloor imaging. It's affected by that. So the hate relationship is kind of it's hard. When during the journey to explore, I'm for some time I'm pretty frustrated. I kind of, this research goes nowhere at the time. Yeah.
And
So-
it's also, if I can step in,
Hi, Leo.
I want to congratulate you because you have shown to me wonderful results that make me very proud of you and
Thank you. You and Pastor also do like very hard work.
I'm
project as well.
very impressed. But if I can answer Chris' question, he is frustrated because we have been extremely unlucky with publication, despite very good and hard work from Zach, because since it's a interdisciplinary field, anytime we send a paper to be published, we receive two conflictual, or three conflictual review. One is very happy, and one is very bad. Usually he mix it up because when we put more emphasis in the seismic part, the seismic person is very happy. When we put emphasis on the oceanographic part, the seismic person is not happy, and they ask more data or more to cultivate more the ones of the other field. So it's difficult to pass this message because this field is so interdisciplinary that there is little knowledge among the two community about this. And Zoo have done a very nice work, but so far it's been not lucky with publishing the result, mostly for this reason. So this is why he hates, because he's not getting the reward he deserves.
Okay.
Not yet.
Yeah. For example, when we publish just on the processing for the seismic part, our paper was published right away because we didn't touch the oceanographic part. It was just a processing effort to improve the quality of data for the seismic aspect on the water column. Anytime we mix the two things, we receive this conflictual revision that also frustrates me.
Mm-hmm. But anyway, I want to highlight the two things encouraging side. There was two moments. I think it was very exciting moments for during the Zheguang's effort in research. The first moment, he spent a lot of time to look into the data, try to find the ocean features. In the moment, when he calculate the spectrum and find out this spectrum had the same slope as what people would expect for internal wave. And so there was a moment was very exciting. We say, we find the internal waves in this area. Okay, so we're convinced we find the internal waves, or we were convinced what we observed were internal waves. The second moment is he was able to went into to look in the seismic data, and it was not in what we previously thought about to do. We didn't think about to look into the seismic data. And he was able to find like during that area in that time window, there was an eddy passing by, and they come up to give a very nice explanation about the temporal variation of the diffusivity he calculated. So there was a moment everything come to agree, and was very exciting as well. So I think Leo, we should be in good shape to look forward to seeing the paper to be accepted.
I'm very happy. I think he did a very good job. That is my opinion.
So, and you know, this area has a lot of near inertial motions at the surface, and you know that actually may radiate near inertial internal waves downward. So you would also expect maybe some increased diffusivities in the thermocline area. Have you noticed any of that? Looking at your plots, everything looked really like bottom intensified. And are the slopes of do you find the same slopes in the shallower area? So maybe 200 meters is too deep already, maybe.
For the slope, I didn't show the results for those slopes, but they are kind of have a similar slope. To answer your question, in fact, all the curvature, most of the curvature in this region have this slope, so they're probably dominant by internal wave fields. That's our guess.
And did you look at like you can? I mean, maybe if you can do some more filtering, or maybe you already did that. Do you see some peaks at certain modes? So if you know the vertical stratification, from that you can you solve the Sturm-Liouville field equation, and you get the eigenfunctions that all have different wave numbers.
Yeah.
So do you see sort of a selection process in that, looking at the spectra?
I didn't do the analyze for the vertical trace, so I am not sure so far. But I think that could be a direction to try.
I mean, yeah. I mean, if you solve the Sturm-Liouville field equation, you're looking for standing internal wave modes.
Yep.
That only have a horizontal length scale.
Right.
So
we haven't do that. All the spectrum I get so far is based on tracking the curvatures and analyze the spectrum.
Right, but then the peaks in the spectrum maybe correlate with some vertical modes. That's my question.
Maybe, yep. But we haven't dig into the individual peaks of those spectrums.
Yeah.
Right now we kind of look at showing the overview of what it looks like. Yeah, that's a very good direction to go. Thanks, Martin.
Okay, well, let's all thank Zheguang and Likun for doing this for us, for those of you who are left. And we usually leave the Zoom open if anybody wants to talk further. So thanks again.
Thank you, Chris. Thank you for having me.